Good afternoon, this is Schweitzer and AP Test Review Laboratory Concepts. These are, in my opinion, some of the most common lab concepts that are, if you plan on doing wellness tests, need to be pretty well understood and be able to anticipate seeing these types of questions. Okay, first one. A lot of these tend to surround around stoichiometry. I consider gravimetric analysis to be somewhat like stoichiometry. But that being said, just a quick preview. What is stoichiometry? Again, what is gravimetric analysis? And of course, you'd want to try these questions on your own, and then, only then, check your answers. Watching me do it isn't going to do you much good. So what is, in the nutshell, what is gravimetric analysis? Well, ultimately we have a substance, whether it's known or whether it's unknown or its concentration is known. We're going to put this substance is dissolved, and we're going to take this substance and react it with something to cause it to become insoluble. So dot plus X forms this new substance. That new substance then precipitates out of the solution, leaving behind stuff that was dissolved. When you filter this thing, then the stuff that's dissolved, of course, goes through the solution, and the stuff that is solid goes to the bottom, is filtered out and stays in the filter. You then can take your stuff and you can dry it, and you now have a sample that is of a known entity, which is that. And of course, if you have a known quantity of those, you can figure out stoichiometrically how many of the dots you have. And they'll do different variations of it, but that's basically it. So this problem says an unknown concentration of lead 2 ions are dissolved in water. In order to determine the concentration, 0.05 molar sodium chloride is added into all white precipitate stops. The NaCl is added in 3 different times. Each additional 12 milliliters. After each additional NaCl, the student waits 5 minutes before adding a second and finally third NaCl solution. After that period of time, the precipitate is filtered out and dried. Alright, so it's giving you a list of information, stuff we did. Stuff should kind of make sense. Radial chemical reaction taking place here. Alright, well, so we have PB. I'm going to use the net ionic version. Two, determine the molarity of the original lead nitrate solutions in here. Okay, so that's our overall goal here, I guess. Let's see what the questions say here. The following questions are to walk you through. Number 2, try without these questions first. Okay, so makes sense. We're going to try and say, okay, I want to know what the unknown molarity is. So I'm going to just work this out and then we'll see what happens. So I want molarity. Alright, so that means I need molarity equals moles per liter. That's what I want. I need these 2 things. Now the original volume for this thing was 24 milliliters. So let's do this right here. Equals 0.024 liters. I need the moles of the stuff in that thing. And then I'll know, divide by the volume, original moles, divide by original volume, give me original concentration. So I know how much of this I have. And I want to know just how much lead I have. The lead that's here actually came from here. So in this situation, says the mass of filter paper and lead 2 chloride is 2.9 grams. So I'm going to take this guy in 2.9, subtract off the 2.0 gram filter paper, gives me 0.9 grams of actual PbCl2. Now I got to figure out in this 0.09 grams how much actual lead is in there. You could use percent by mass. You could use stoichiometry. I did a percent by mass in an earlier video, but I'm going to use stoich here. Dot line, get rid of grams, go to moles. This is lead chloride, 1 mole. So we're going to add up the molar mass of lead chloride. And lead is, I think I have a periodic table here, I think it's 207. So lead is 207, and then the chlorine is, let's just go with 35.4, and we'll add that up. So 207 plus 35.4 plus 35.4, and I get 277.8. 277.8. Alright, so obviously we have less than 1 mole. Quite a bit less than 1 mole. We have less than 1/100 of a mole. But let's divide it out. 0.9 divided by molar mass is 0.003. Now this is of lead chloride, and there is 1 lead in every 1 lead chloride. PbCl2, Pb. This is a math piece that I probably don't stress enough to show. And there's a good possibility, or I should say good, there's a possibility that people will mark things wrong if you don't put those 1-to-1 ratios on there. 0.003 moles of lead. Alright, and then from there, just convert it back to grams. I'll put that mass here. Actually, do we want moles? We want moles. We don't need grams. If I were doing a percent by mass or something like that, I could go back and get the mass of just the lead. All right, anyway, so now I'm going to take my moles and put it right here. 0.003 divided by the 0.024, and I'm going to get my original molarity. Divided by 0.024, and I get 0.134 molarity. 0.134 moles per liter. Okay, so the next questions we have here would have just walked us through. I think from what we did there, all of these questions we did. Now this one here is how many moles of lead to solid are present in the filter. Turn the moles present in lead by stoichiometry or percent mass. I did stoichiometry. You should be able to do both. Using the mole lines, determine the original solution concentration. All right, we did that. 3. So this is a fairly good little problem 3 here. So some of the solid slips through the filter as you filtered it. How will this affect the calculated concentration of the original solution? So in this case, molarity equals moles per liter, and in this case, when we filtered it, some of our original solid went through. So the mass of the PbCl2 is lower, which causes our mass of Pb to be lower, which causes our moles to be lower, which causes this to go down, which causes this to go down. Therefore, our molarity is smaller. You should be able to describe that particular phenomenon. All right, general titrations. Alright, a student is looking to determine the percent composition of an iron sample of an iron containing block. The iron containing is titrated against standard KMnO4. Now we did this one in lab, this kind of this experiment, and there's a reason why, because it's very common, and this wouldn't be surprised if this exact reaction shows up. So it says relative to the lab, determine the iron percent mass you titrated before the trial collected and the data below. So it looks like we're going to have some data coming up here. Let's flip the next page. Alright, so again they give us data here. You got several trials that took place here. And it wants to know percent iron. Once again, you could try this particular thing A and B are walking through, determine the moles of iron, determine the percent mass of iron. Okay, let's do this. Alright, so we did several trials, and of course you'd want to look and see, okay, well we got two trials that are fairly consistent, one trial that's a little high. There likely would be a question asking why this one is higher than the other ones. So, you want to consider various issues or things that could have gone wrong. I'm going to let's just use trial 1. Trial 2 are very similar, so I'm just going to use one of those two to do my particular work with. I wouldn't not want to use the outlier point of the 29. Determine the moles of iron titrated in the sample. Okay, so in this case, I'm not going to do a known unknown table. You could do that. Remember, and I try to stress to people that this is not a source of work, and I have marked just this wrong because you have to show your work. I'm going to solve for the moles of my known, and that is going to be in this guy. 22 milliliters of my KMnO4 is the known. The concentration of KMnO4 is that. So it's 0.0196. There's 3 sig figs. Should probably have 3 sig figs there. So I'm going to hold 3 sig figs. 0.022 solve for the moles. Alright, 0.0196 times 0.022, 0.000431. Alright, so moles of, in this case, now it says KMnO4, but we're just using the MnO4, the K as a spectator. That equals that, MnO4 negative. And then it is a 1 to 5 ratio. So just like we'd show the 1 to 5 ratio, we'd want to show 1 to 1 ratios as well. Alright, times 5. 0.00215. And that would be moles of Fe. And I think that is my answer. Make sure when you do a calculation, you designate your answer. Alright, percent mass of iron in the original sample. So percent mass is mass divided by total mass times 100. Alright, so in this thing we have total mass. That's given here, unknown sample, 0.25 grams. Then, so this is going to be 0.25 grams is my total mass. That's got the iron in it, and it has other stuff too. I want the mass here. So I'm going to go 0.00215 moles of iron, and I'm going to get rid of the moles of iron, go to grams of iron. 1 mole, 55 grams, and times 55 equals 0.118 grams. Alright, that's going to go up top here, 0.118 moles, grams iron. Divide them out, don't forget times 100 equals. Alright, divided by 0.25 times 100, and of course looks like we got let's try this again, 0.118 divided by 0.25 equals 0.47 times 100, saying 47% by mass. Okay, looks good. It's 0.25, so it's about almost half. So 47.2%. Fe. All right, if a known sample is if a known sample is 12%, what is the percent error? Okay, so percent error is essentially what we call percent change. And you can Google the formula if you want, if you don't know. What I typically do is you want to do the difference between what you got and what you're supposed to get. So this is what we're supposed to get. We got 47. So the difference between that is 47.2 minus 12%. Now, we're higher than we're supposed to be, so we have a positive error. If we're lower than we're supposed to be, we have a negative error. Sometimes you'll see an absolute value sign on percent error, just meaning they want to know just the change. But I've seen various ways this is done. So, and then I divide it by what we're supposed to get. All right, and there we go. We could also do the same thing with the actual mass itself, or you get different. It might vary some, but 47 minus 12 equals 35.2% difference. So the size of the difference divided by the actual size of the number. So we have a significant size error here relative to the size of the number. And we multiply it times 100. So in this case, we get 35 divided by 12 is 4. Did it wrong. All right. That math there is 2.9 times 100 equals 293% error. So keep in mind that if we had a difference of 12 units, then we'd have 100% error. 24 units difference, we'd have a 200% error. And so we're getting awfully close to 300% error. Which the following errors would cause the percent error you calculated? Okay, so this is pretty common. Now we have a large percent error. So in this situation, if we look at the math on this thing, so its percent mass is of iron is the mass of the iron divided by total mass. So we need to know an error that's going to either cause this to go up or this to go down. Okay, student titrated past the equivalency point, causing too much manganate to be added. Okay, this will cause the permanganate to go up, which will cause the iron to go up. This one's a yes. sample of iron contained an inert impurity at the time of weighing. All right. Well, this would cause, well, in this case, I guess inert impurity, we know it contains some other things, and that's going to contribute to the overall percent iron. This, however, if anything, would drive this number up and cause the iron percentage to go down. So that's not going to have any effect. That is not the desired air we would want. Extra water was added to the iron sampling for the purpose of dissolving. This would mean that we're adding water after we weigh it, so this number is locked. And the mass of the iron would not be affected by this because the titration is adding more water will not affect the titration. So also just this isn't going to have an up or down effect. It's just going to have no effect. Number 2, we titrated MnO4 negative, which is starkly, this stuff is purple. Why are we always looking for color to reappear or to stick around, or what does this mean in layman's term when color remains? All right, well, in this situation, we're looking to get rid of the iron. And for every 1 iron, we react with, looks like, I think it was 5 irons for every 1 MnO4 negative. So the iron converts MnO4 to a colorless product, Mn2+. So we know that when the purple disappears, also means that this stuff is gone. And it means this is now our limiting reactant. And technically, if the purple disappears, means we're consuming more iron, I should say. Never mind, that's not the limiting there. Hold on a second here. So as we're adding this stuff, more and more iron is disappearing. And once the MnO4 stays around, it means that all of this is gone. All of the iron is gone, or you might say the iron is now limited out to 0. Technically, if you keep on going and your purple appears, technically we have overshot the particular process. And a really careful precision measurement, they might back titrate to get that purple to remove. And just to be clear. But all right, number 3, we standardize the permanganate solution with oxalate ion. The term standardization means to determine or verify the solution concentration for use in lab tests. Otherwise, other than the obvious reason for knowing the concentration, why is a standardization needed? All right, so we're testing this thing with the MnO4 negative. And this stuff has been, sitting on the shelf for a while. So we want to make sure that the actual concentration is what the concentration says it is. But it says other than that reason. Well, the reason why we want to know the concentration is because this stuff could have, over time, decomposed. Meaning that some of the active ingredient may have deactivated and therefore isn't working. This would drive up the amount of MnO4 that you need when you're titrating your known versus your unknown. Your known is your MnO4, and of course you have molarity, you have your moles, you have your liters. That's gonna, the concentration we think we have isn't what we think we have. So it's less. So that's going to drive up the volume of this, which is going to drive up the apparent moles, which is going to drive up the iron, okay, which is going to cause the percent iron to look higher than it actually is. Another reason why would be if, maybe this stuff is what we call hygroscopic, which means it collects water from the atmosphere. So in that case, once again, it's going to cause my molarity to be too high in air, cause the same phenomenon. All right, a student is titrating until the reaction turns purple-pink and ends up titrating way too long. How does this affect the answer? All right, so again, that's going to drive up the volume you use, drive up the moles, drive up the iron. Explain the cascading factor. So moles higher, iron higher, and then of course the percent mass is the iron divided by the total. That's going to cause this to be higher, which causes your percent air to look higher. All right. Next lab. Hydrogen peroxide decomposes by the following reaction. Okay, so in this case, we have a gas collection lab. So gas collection would be is basically, for all intents and purposes, stoichiometry lab. 10 grams of a 3% mass of hydrogen peroxide solution is decomposed at STP, answering the following questions. The vapor pressure of water is 23.8 millimeters of mercury. All right, so a couple things I'll mention here. First of all, as you get started, you should realize the vapor pressure that they're giving you this. So when we collect over water, so let's imagine just generic scenario, and we've now had a full tank of water here. This is over a pool of water, and we've dropped in some air, gas bubbles, and created a vacuum here, or I should say an air pocket. What's in this air pocket? Well, now typically I would want my volumes to be equal, and that way my water level inside equal to the water level outside. When it's like when that is the case, then the pressure inside equals the pressure outside. So whatever pressure we have on the outside, which we're saying is 1 atmosphere about, I'm getting that from right here. But it might be a little different. So my total pressure is, so the total pressure in the container is 1 atmosphere after gas collection. What is the partial pressure go to? Keep in mind that 1 atmosphere is equal to 760 torr. So they might be dealing with this thing in torr, or it might be in millimeters of mercury. These are on your laminated sheet, and this is the same equivalence. So I'm going to subtract off. So my total pressure, in this case, this is Dalton's law of partial pressures. The partial pressure of the gas plus the partial pressure of water. So mine equals the partial pressure of the gas plus the partial pressure of the water, which is 23.8. So a pretty simple calculation. Just going to subtract off the 23.8 to get my new pressure. 760 divided by 23.8. 760 divided by, subtracting 23.8, 736.2. millimeters of Hg. All right. I think that's the end of that page. Let's continue on. All right. What would be the total mass of hydrogen peroxide present in the solution shown below? What would be the total volume of oxygen produced? All right, let's go back and grab some data here. So we got, so my formula as well, total mass of the stuff here. Right. So it says a 10-gram sample of 3% by mass hydrogen peroxide solution is decomposed via the equation provided. Answer the following questions, and the vapor pressure of water is, okay, so first question is it wants the total mass of actual hydrogen peroxide. Well, we have 10 grams, and it's 3% by mass. So letter B on the other side is the total mass. I'm just going to take 10 grams times 0.03 is going to be that guy. 10 times 0.03 is 0.3. So I actually only have 0.3 grams of H2O2 present in the original solution. And then it wants to know the total air pressure, total amount of volume of gas that's produced from this decomposition. Okay, there's my equation right there. So I'm going to just flip over so I have more room. So this is just a stoichiometry problem. I have H2O2 goes to H2O plus O2. I want to put a 2 here, and a 2 here, 1 there. Okay, so I have 3.3 grams of this stuff. So this guy is going to go to grams, to moles, and it wants to know the volume of oxygen gas produced. So I'm looking just for that, and volume-wise. Okay, add your molar mass up that 32. This is 34 to 1. It is a 2 to 1 ratio. This gives me my moles of oxygen. Divided by 34, divided by 2, and we get 0.0044 moles of O2. And then we're going to flip this over to volume. It does say it's STP previously, so I'm going to use this calculation. 1 mole is 22.4 liters, or you just got to use Pfeffner's. I think we're at that. So times 22.4 equals 0.0988. Right. 0.0988 liters. Alright, in this reaction we used iron ions, and that kickstarted the reaction, so it is a catalyst. If the iron was used in the reaction, an iron is orange and yellow, why do we not see that color disappear over the course of time, or the reaction? It's because catalysts are not consumed in the reaction. They're there in the beginning and they're there in the end. A student runs this experiment and some water spills in and it's not recorded. How or what effect will this error cause on the outcome of the percent be specific on the error? So one issue with this is sometimes kids will say, oh yeah, that's going to cause a problem. What we want to know is how will it affect up or down. So in this case, it says how will it affect the outcome of the percent H2O2. Alright, well, so percent H2O2 would be, let's say, the quantity of H2O2 divided by the total. Alright, now whether you do molarity or percent by mass or percent by volume, it's not going to matter. So when we decompose this thing, the water is not decomposing. So the amount of actual gases produced should be the same. But the total volume will increase, assuming that that is where they dropped it in. That affected that bottom number there. That, take your original moles or volume, or whatever you need to do to get that top number, divided by this guy getting bigger is going to cause the percentage peroxide to be dropped. Okay. All right, finally, last one here, again, pretty common experiment, actually the last one, empirical formula. A copper strip has an iodine added and heated, causing a reaction to take place. After the reaction took place, the mass was 2.59, and the chemicals cleaned off and remassed at 2.45. What is the empirical formula given the data show all work? Okay. So in this case, we have copper and iodine. So when we run these two together, we have a copper strip, putting iodine on there, and we heat it up and it runs. It's either they're going to form copper iodide, copper 1 iodide, or it's going to form copper 2 iodine. So in this situation, 1-to-1 ratio or 1-to-2 ratio. So we want to look and see which one is it. All right, so in the beginning we have a 2.5 gram copper strip. So I wanted to figure out the copper, and I want to figure out the iodine. This can sometimes be the trickiest part of this whole deal. The rest of it's just stoichiometry. So we took this strip and we had the copper on there. This strip weighed 2.5. Then we reacted and it showed that this thing had an additional 0.09 grams of iodine that reacted. So this guy is going to be 2.59 minus 2.5, showing that we have 0.09 grams of iodine that's on that strip. And then this guy is going to be the 2.5 was all the copper minus the iodine that reacted. Now when we did that, we pulled off the substance. This substance had both copper and iodine in it. So minus the 2.45 means now we lost 0.05 grams of copper. So now we're going to flip this over to moles, grams to moles, and we'll start to see potentially our particular ratio. 1 mole of copper is 63, but let's just check this out, what iodine is. Alright, so the 126.9 and the copper is 63.5. Alright. $126.9, 63.5. To the math, 0.05 divided by 63.5, good enough, 0.000787. Alright, so 0.000787, holding 3 sig figs. This one is 0.09 divided by 126.9 equals, now again, 3 sig figs is what we want to hold. This is 0.000709, and we would note that they're pretty close. I would be leaning towards that guy. To show the actual math, I divide by the smallest one, which happens to be the 0.000709. This guy will give me a 1. One of these guys, one of these guys, divide out the other one, and it's going to be awfully close to 1 as well. This will equal approximately 1. And we can't have a 2 anyways, it's not one of our options, but copper would be 1, and it says give the empirical formula. So this is not it yet. CuI is 1. Alright, what color is iodine vapor? Should be aware of that, at least for this particular lab, that it is purple. I have seen many strips that were not cleaned carefully of copper iodine mixture. How would this error affect the empirical formula? Okay, so let's look at an error and see how it's going to affect it. So really, there's only 2 things that can be affected. We're going to weigh this thing. Well, the first weight is unaffected. The second weight is the weight is the 2.59, and the third weight was the 2.45. 4, 5. So the first weight will affect the iodine right here, and the second weighing would affect the copper right there. None of the weighings we're doing, I think, are going to affect the starting one, unless the air, I guess, does that, has something to do with that. But so when I look at an error here, I'm looking to see what actual numbers that affected. Okay, so 5, it says the student was working very hard and over cleans the copper strip prior to the last massing, causing lots of copper to be removed that did not actually react. So that causes this number to be lower than it actually is. Okay, that's this number right here. This one goes down, causes this number to become bigger, causes the copper to become bigger, and this will cause, how affects your answer, causes the copper to go up and conversely the iodine to go down. That's how it would affect the ratio. All right, I think that's the only one we have there. All right, Beer's Law, another extremely common phenomenon. We should be able to function with Beer's Law really in two different ways. One, understand the fundamentals of Beer's Law. That means that we have a vessel with light shining through it, and stuff gets absorbed, and then only some light is through. So we have two ways we sometimes see this percent transmittance, or absorbance. And there is actually a Beer's Law formula that's on your laminated sheet. The absorbance is equal to the what they call ABC. C is just a constant that links everything together. B is the base length path. C is the concentration. Now, how do you know what unit B would be in? Well, if they give you a constant, it'll have units on there, and inside that constant there'll be a unit of length. Lots of times it's centimeters, which means that this would be in centimeters. And typically that base path is 1 centimeter. Pretty simple mathematics. I haven't seen it come up in a couple of years, but if they give you A, they give you B, they give you absorptivity, you could show it solve for concentration, vice versa. The last way we do this is maybe more common. It's to create a Beer's Law plot, in which case they give you a line here, and they may have percent transmittance here, or concentration here, and they'll give you a y equals the equation showing that they could have these backwards too. I could have them backwards. It doesn't matter at this point. Well, you could look on the graph and see what they have. So let's read the question here and see what it says. Copper is a component of brass. The quantity of copper in brass was measured by first reacting the brass with nitric acid, then measured with the quantity of light that passed through the sample. The light that passes through the substance can be measured percent transmittance or absorbance. They are inversely proportional, but absorbance is not a percentage, so not a 100 scale. So yeah, so as one goes up, the other one goes down, but it's not proportional. The series of known copper solutions were tested for absorbance and plotted to create a linear relationship between the linear relationship by that there. All right. Let's see what the question says. All right, the actual mathematics shown below is provided. Below you are provided with a blank graph. Roughly sketch the graph that might look like this. Okay, so only draw the line, do not set to scale. Okay, very rough graph. So just what is Beer's Law essentially? As concentration goes down, absorbance should go down too. So it should something like that. Higher concentrations have higher absorbances. Alright, this next guy here is it's giving us an absorbance, which is the absorbance is going to be the y component. Solve for the concentration, which is x. And if you look at this guy, so 16.1, I'll do it on the other page. So I'm going to use this formula. 16 is the absorbance, equals 32x plus 0.0032. Plug it in. Simple math at this point. 16 minus 0.0032 equals, divided by 32 is 0.4999, and that would be my concentration. Holding 3 sig figs. All right. Number 3. Beer's law is a very useful tool. Hold on, 2. A student claims since the solution of copper is blue, we should be using blue light to shine through the solution. Justify or nullify this claim. So this is getting more common over the times. And what light should you use in this thing? Well, they might give you a graph showing all the various colors of light. And they might even go beyond the scope of visible, and they'll show what range of light a particular substance is absorbing. This will be listed in nanometers, and you want to take the one with the highest spike. There might be another one here. Take out the highest spike, that is the most light is absorbed, and that's what we want to use. Now for this problem, since this thing is blue, it means it's actually reflecting blue. So we would want to nullify this claim, and this is the light that we would not want to use. We want to use a different color, maybe red would be more absorbed. Remember, blue is RGB are our standard lights. Red, green, and blue. So we would want to use one of those two instead of green, instead of blue. Beer's law is a very useful tool for determining the concentration of stuff. Give one example where Beer's law is not the best technique. Essentially, the best option is one where there's no color. Or maybe it's a solid. Solids would be less useful. Some solids could be dissolved, and then utilized. But the amount of light absorbed by a sample that is actually traveling through is given by the following. What does L stand for? As I mentioned here, it's another way they look at it. So this looks a little weird here, right? This is A, this is B, this is C. That's the length of the base path. All right, acid-base titrations. Super common, right? We want to be able to solve for standard molarity things involving acid bases. We want to solve for molar mass, and we want to be able to interpret this particular graph we have here. Now again, whenever we're doing a titration, there's two main things we can solve for. One is molar mass. This is going to be original grams divided by original moles. This would typically be given. We need moles, which is where we use the titration to get. Or molarity, which is moles, original moles divided by original liters. This is typically provided. We want to solve for that, solve for that. You should be aware when you see one of these that this, of course, is the equivalency point that we use to find our moles. You also will notice that my little known unknown table is becoming much less useful. And this is, of course, is not a source of work. But I'm solving for moles, so I don't even typically need that. But that is just going to be plugged into the moles here or the moles there. And we're going to go. Alright, so at this point, I want to know what is the concentration of unknown acid. So I'm looking for molarity is equal to moles per liter. And this is the work I want to show. You are charged with the task of determining the concentration of an acid. The student measured out 30 milliliters of the acid, so right off the bat they're giving us this 0.03 liters. The burette was rinsed once with water and filled with burette, molar NaOH. The pH was monitored, and the following graph was produced. So in this situation, my known is 0.1, and my volume is 0.04. Solve for the moles. The moles equal to 0.004. This is 0.004. Divide out. 0.004 divided by 0.03, and I get 0.133. Alright, unknown acid is, I'm not sure where that, I'm solving for x. X is going to be 0.133. 0.133. Actually, my brain lapse there. That is the moles. I just did the math there. 0.133 moles per liter. And that's my answer. Make sure you indicate your answer. Indicate if there were any mistakes that occurred as the result of the student's actions that could have been affected the lab. Okay, so they described above here a few things, and I asked kids to just pick something. I think there could be a couple. The one I think that I was most commonly looking for is that it says here they rinsed the beer with water, but they didn't rinse it with the 0.1 molar. So that is going to cause an effect. They're going to, inside the beer there'll be some more water. We want to rinse that. So rinse with 0.1 molar NaOH. Right. There could be others there. I know there are others because is the weak acid strong or weak? Explain. Good question. All right. The way I would do this problem, the way you should do it, is that you would look at your titration graph. Now you know at the equivalency point. Right, there it is. Now, you should also be able to draw a picture of these things. At the equivalency point, I have a pH, all right, that looks, well, first of all, it's basic, which is fine. So our unknown acid, HX, is being titrated against a base to produce X negative plus H2O. Now this would be an excellent question. Write out the net ionic equation for the titration. Alright, well, this is an acid, and therefore this is a base. And at the equivalency point, all we have is this stuff right here. So this stuff appears to have a pH right around 8. This is a weak base. Therefore, that means this was a weak acid. And that's how you'd want to describe that. The conjugate is a weak base. Therefore, the original acid is a weak acid. Next one. Source of error unknown to the students. A second student added a little water to the acid just prior to starting the titration, but after the original 30 milliliters was measured. Okay, so let's look at the original formula. Molarity equals moles per liter. And what they're saying, I think, is that this is artificially driven up. So we're diluting a little bit. This would not be affected, but in the end, it's going to cause my molarity to look like it's smaller than it is. So essentially we have a beaker here with, you know, some stuff in it. And what's going to, if you add some water to it, it's going to perceive to be less concentrated. All right, next one. A 5-gram sample of Na2S is dissolved in 25 milliliters of water and the pH is tested. In what range might you find the pH? All right, this is a pretty tough question for kids. Few things you want to note is that when Na2S is dissolved, it splits into Na plus ions and S minus 2 ions. This guy is the conjugate of NaOH, so it's neutral. This is the conjugate of H2S, so it's a weak base. This is a weak acid. Alright, so it should be in the range likely right here. If you were to calculate the probable pH on paper, what might one piece of information you might want on paper? So, well, in this case, I want to know in this situation, well, I have 5 grams of stuff dissolved in water, so I'd be able to get the concentration that I could get. I have that information. So when I do my math on this thing, in order to find the pH of this thing, I need two things. I need a K value and I need a concentration. It appears that this is already provided, so equilibrium constant is the piece that I'm still missing, Kb likely. For the Sn -2, lots of times it would give you the Ka for HCN. Alright, if you were to titrate this salt with 0.1 more NaCl, what volume might you expect to reach equivalence? Okay, well, first off, we got to know the moles of the S-2. So this guy is going to be H plus S-2. Two of these for every one sulfur to give us this. Alright, so in this case, let's get the moles of this. 5 grams. Now that's the whole Na2S. So grams to moles, I want the whole molar mass of the whole thing. Alright, molar mass of sodium is 23. I believe and there's 2 of them. I believe this molar mass of sodium is 32, but I'm going to just check on that quickly. Sulfur is about 32.0 and the sodium is looks like about 23 close. Alright, add all that up and we get the total mass of 1 mole. $78. Alright, 78 grams per mole. Alright, how many moles do I have? Well, 1 mole is 78. I have less than 1 mole. 5 divided by 78. 5 divided by 78 equals 0.064. 0.064 moles. And at that point, this is the moles of H, will be Na2S, which equals the moles of sulfur, 0.064 moles of sulfur. But for every 1 sulfur, I required 2 hydrogens. And this would give me the moles of hydrogen that I need. 0.128. And at that point, we have 0.128 moles. Okay, so let's do concentrate once volume. Saying it's 0.1. So I need 0.128. I need more than 1 liter. So molarity equals moles per liter, 0.1. I need 0.128 moles. Solve for that. It's going to be quite a bit more than a liter. So I'm going to take this, solve for the liters, divide by 0.1. I get 1.28 liters. And that is my answer. Liters equals 1.28 liters. We certainly wouldn't want to titrate that much. At least not in a burette. Sketch below the neutralization titration if doubled. If double the quantity of acid in number 11 is added. So a couple things here that I would point out about this. The question is a little bit iffy, I guess, as far as what they want here. But when you titrate, one, we're going to start out acidic, because never mind, we're going to start out basic, because Na2S is basic, not super basic, just a weak base, somewhere around 9, let's say. Then we're going to titrate, and every time we add, we're going to first H plus S negative 2 will produce H S negative 1, and then H plus H S negative 1 will equal H2S. So we're going to have two equivalency points. So it should look something like this, like that, which end in a weak acid. Okay. Two equivalency points. This one here at this point, the only thing present is HS. Only thing present right here is H2S, and we're getting excess H plus ions, causing our acid to go down. And we are done.